All right, so welcome everybody to the second week of the ISIM. My name is Patrick Tolksdorf. I'm here today as a guest speaker, and I'm one of the co-authors of the ISIM lecture. So this week we are going to talk about the so-called H-infinity calculus. And we started already in lecture 4 with the topic or with the Laplacian, and we constructed somehow like an elementary functional calculus for the Laplacian, and then extended or generalized this whole functional calculus to sectorial operators. And we saw already in the last week that, for example, like deep properties as the Calderon reproducing formula for the Laplacian takes over to all sectorial operators essentially. So we also had another property of the Laplacian, and I will formulate it here as a question. Namely, if we plugged in the Laplacian into some bounded function, it was a bounded continuous function, then we saw in lecture 4, it was theorem 414, that this is again a bounded operator for any bounded function f. And we also assumed it's continuous, and let's say if we have a sectorial operator, we could formulate this here as a driving question somehow here for this lecture. So does this property here for the Laplacian takes over to all sectorial operators L? And let's say we take a function, an angle phi between the angle of sectoriality phi L and pi. Okay. And so the first problem is already whether this expression here makes actually sense. So first problem is that maybe f is not regularizable. So let's say and this might not always be the case for any sectorial operator, but it's regularizable if, for example, L is injective. So we could formulate this question here for injective operators. Namely, if L is injective, then we have a certain regularizer. We saw it already earlier, namely the function E, which we shall define as z over 1 plus z squared. This would be a regularizer here for a bounded holomorphic function. Okay, so if L is injective, do we always have this property that if we insert the operator L into a bounded holomorphic function f, whether this is always a bounded operator? The sad answer is no, in general. So we saw last week that the Calderon reproducing formula takes over to sectorial operators, but here, unfortunately, this property is not always true. Okay, but we saw already there are some operators which have this property, for example, the Laplacian, and this leads us to the study of operators which have this property. So this leads us, let's say, to this next section, or to the first section of this lecture, maybe the notion of a bounded H-infinity calculus. Okay. So if a sectorial operator here has this property, then we say it has a bounded H-infinity calculus, and we're going to notice this here in definition 7.2. So in the ISOM lecture, we have a notation 7.1. Namely, H will always denote a Hilbert space with inner, so H is Hilbert, and we have an inner product and a norm on the space. And I will just skip the indices here. And also, the regularizer E will always be this function here. All right. So let's say we have an injective operator L. It shall be sectorial as well. And then we say that L has a bounded H infinity calculus of some angle phi and this angle phi is always between the angle of sectoriality phi L and the number pi if we know that there exists a constant C such that for all bounded holomorphic functions on the sector S phi, we have the properties, namely that first of all, f of L is a bounded operator, and furthermore, that we have a bound, namely that we can control the operator norm of f of L by some constant C times the supremum norm of the function f on the sector with angle phi. All right. And so this angle phi is always bigger than the angle of sectoriality, but we could take, for example, the infimum over all such angles such that this property holds, and this is called the H infinity angle of the operator L. And this is denoted by phi L infinity, and this is the infimum over all phi as above. So we see that, for example, this H infinity angle is always greater or equal than phi L, but it could also be, for example, like at the first sight, it could be strictly larger than phi L. And we will see next week that actually both angles coincide. But we can't see it right now. Okay. So some remarks are in order. 7.3. Namely, at the initial question, I asked that whether only f of L is a bounded operator for any f in H infinity. And here in the definition of the H infinity calculus, we also have this norm bound of the operator norm by the infinity norm of the function f. And actually, this is a bit redundant. Namely, one can show that L has a bounded H infinity calculus. Sorry, this is already part B. Let's first write here part B. So L has a all right. So let's say if already this property holds that f of L is a bounded operator for any bounded holomorphic function f, then already this estimate here follows. So if already for all f we have the property that that f of L is a bounded holomorphic is a bounded operator, then we already know that there exists a constant C greater or equal than 0 such that this norm bound also holds for all bounded holomorphic functions. And this you will see in exercise 7.4. So essentially, the boundedness property here suffices, and then you will get also the norm estimate here. Okay, so see exercise 7.4. All right. We have a second remark, which is now called A. Namely, if you have a bounded H-infinity calculus, then we know already that first we know already that the functional calculus is an algebra homomorphismus, and if you have this norm bound here, you know that it's even a bounded algebra homomorphism. So if L has bounded H-infinity calculus, then the mapping which goes from H-infinity of S phi and maps to the bounded operators on H, and you map F to F of L, is a bounded algebra homomorphism. Okay, and the third remark is that this notion here of a bounded H-infinity calculus, it was actually invented by Alan McIntosh in order to solve essentially the Carter square root problem, which we do in the last lectures here. So this notion was invented by Alan McIntosh. All right. Okay. And we have a first, let's say, question, namely, if you want to prove something about the H-infinity calculus of some operator, then it would be nice if we have some formula at hand. And it's not so easy to really work with regularizers, let's say, but it would be easier if we simply could use the Cauchy integral formula, let's say, or the representation formula here for f of L. And this is, by definition, we could do this if we insert L into an H0 infinity function. And in order to make this somehow accessible, we have the following lemma, which is called the convergence lemma, which is also due to Alan McIntosh. Okay, and we assume that that L is an injective operator, and let's say sectorial, and we take some angle between the angle of sectoriality of L and pi. And then we further take some functions fj, which are bounded and holomorphic on this sector of angle phi, and we further assume that the sequence of functions uniformly converges of every subset of the sector here. All right. So these are here our assumptions. And then the conclusion is that we have, or what we want to know is, for example, if we plug the operator L into each of these functions fj, and also they converge to some function f, and then we also want to insert the operator into the limit function f, and then the question is, how are they related essentially? And this could help us, for example, because if we have a given h infinity function, we can somehow push it down a little bit at the origin and at infinity to make it let's say, to approximate it by h0 infinity functions. We could insert then the operator L into each of these functions and then approximate somehow the application of this h infinity function to L, and then we could find out something about the limit operator. All right, so the assertion here is that first we find that the pointwise limit of these functions here as j goes to infinity, we call this limit function f. It's again a bounded h infinity function. It's again an h infinity function on the sector S phi. And we can also say something about, or we also see that that if we insert L into this this operator into this function fj, we can approximate f of L applied to u as j goes to infinity, at least if u is in the domain of L and also in the range of the operator L. All right. So this is the first part here of this convergence lemma. Moreover, we have two other properties. Namely, in the end we would like to say something about the boundedness of the limit operator. And if you know already, if for example these fj's, if they would be in h0 infinity, then each of these operators would be already bounded operators. Okay, this is something we saw by the very definition via the Cauchy integral. So we would like to say something about the boundedness of the limit operator. And this is what we do here with the two next statements. So we have a statement A, namely, if, let's say, each fj of L operator is a bounded operator on H for any j, and let's say if we already know that that we can strongly approximate a bounded operator T on H by these operators fj of L, so we assume there exists a bounded operator T such that fj of L approximates T in a strong sense. Then the limit operator T here is already given by f of L. And in particular, f of L is then also a bounded operator. All right. So the second property is so maybe, I mean, here we don't know already whether, I mean, we want to say in the end something about the limit operator, and here we have already to know that the limit operator is bounded, and we can replace this somehow by a different property and then conclude that the limit operator is bounded. And this is the following, namely, we assume that that if we measure somehow the operators f of Lj, fj of L, in the operator norm on H, and if this here is uniformly bounded, so if the supremum here over J is finite, then the limit operator f of L is already a bounded operator on H, and fj of L approximates f of L strongly. All right. So this is the first property that we want to have. And let us fix already, or let us state first the first corollary somehow here of this property. This is corollary 7.5. So if, let's say, this norm bound here, which I denote by, let's say, this purple star here, if this norm bound here holds just for H0 infinity functions, then we can carry over it to all H infinity functions and conclude that the operator L has indeed a bounded H infinity calculus. So this is our first reduction to, let's say, only H, or to the property that we only need to establish this estimate here for H0 infinity functions. So if this star inequality holds, but only for all functions f which decay at 0 and at infinity, then this inequality also holds for all H infinity functions f on the sector S phi. In particular, L has a bounded H infinity calculus. Of angle phi. All right, so let's prove first this corollary here, and then we go over here to this convergence lemma and see why this approximation result here is true. And you can think of it somehow as a density result for let's say, for bounded operators. So if you know you have some boundedness estimate of some dense subset, you can carry it over to the whole space. And this is essentially the same what here this convergence lemma says. All right, so let's first prove the corollary. We take some function f in H infinity of S phi, and we want to establish this norm bound here. We want to control the operator norm of f of L by the infinity norm of f. And what we know is that we can already do it for H0 infinity functions. So we need a good approximation somehow here of this function, and then use the convergence lemma in order to carry this estimate over. So let fj be defined as this regularizer E, and we take the jth root here of this function. So the regularizer is again here this function E, which is given by z over 1 plus z squared. And then we take the jth root of this function, and you need to one needs to keep in mind that you take a jth root somehow of a complex number, and you still need that this somehow makes sense. And for this, one would need to see that actually this function e leaves the sector as phi invariant, and then you can still take the jth root of this function. You can read this in a little bit more detail in the lecture notes, and but this property here holds true. And we multiply here the jth root of e by the function f. Okay. And all right. And we see that first this function fj is already an h0 infinity function on the sector with angle phi. So because so the decay somehow here of e carries over here to this product, and so the product here is still an h0 infinity function, and also because if you have some fixed number and you take the jth root and send j to infinity, you know that this converges to 1. This is just analysis 1 essentially, right? So this approximates the function f. And if you do it a little bit more carefully, then you even see that the sequence fj approximates the function f even uniformly on all compact subsets of the sector S phi. And what we also see, so here this is already the first property that we need for the convergence lemma. And you also see that that you can also control the infinity norm, the supremum norm of the sequence fj. So we also need here that the sequence is a bounded sequence in H infinity. And this can be seen as follows, namely fj, so the infinity norm here of the sector S phi of the function fj can be controlled, because it's just this product here, by the supremum norm of f on the sector S phi multiplied by the supremum norm of e to the 1 over j. All right, and here we just have now a real number which is taken to the jth to the 1 over jth power, and this also converges to 1 for j to infinity. So in particular, this is bounded in j, and so this sequence here is a bounded sequence in H infinity. Now we can apply the convergence lemma part B here. And we see, because the infinity norms here of each function fj, they all stay uniformly bounded, and we assume already that we have the boundedness estimate for h0 infinity functions. So in particular, this means that that if we plug the operator L into fj, that the operator norms also stay uniformly bounded. And then we can apply lemma 7.4b, and we see first that the limit operator f of L is a bounded operator on H, and we further see that that we can also control the operator norm here of f of L as follows, namely we apply f of L to some element u of our Hilbert space. Then we can write this here as a limit for j to infinity of fj of Lu. Now this is because of the convergence lemma, because we know that we have here the strong convergence. Now we use the boundedness estimate here for h0 infinity functions, and we get here some constant c, we get, and we insert here this norm bound. So we have here the supremum norm of f on this angle, on the sector with angle phi, and also the supremum norm of our regularizer, and take the jth root times the Hilbert space norm of u, and we get here, for example, because for example, the limit inferior for j to infinity. All right, but this quantity here is finite, and we see that the limit inferior here, essentially it converges to 1, because here only the limit goes to the jth root. So altogether, this here will be just the infinity norm of f on the sector as phi. So we get that this is less or equal, or this is equal to c times the infinity norm of f times the Hilbert space norm of u. All right. And here, in between, we used this inequality star, but just for h0 infinity functions. All right. So this is how we are going to apply this convergence lemma in order to reduce the study of the bounded h infinity calculus to the study of, let's say, this norm bound for h0 infinity functions. All right. So let's prove the convergence lemma. All right. So proof of lemma 7.4. All right. So first, we assume that the sequence fj converges uniformly on compact subsets of C. So from your complex analysis class, you know already that the limit function f is holomorphic. Then you further know that, or we further assumed that the sequence fj is also bounded in h infinity. So in particular, the limit function will be a bounded function. So it itself is a function in h infinity on the sector as phi. Okay. So this is already the first statement here for then. And then the question is whether we have the strong convergence here for elements u in the domain of L, and also which also lie in the range of the operator L. So let's say we take u in this class of elements, and then we know from proposition 2,4e that we can write this element u as, let's say, the regularizer L applied to V. So we know there exists some V, let's say, in the Hilbert space H, such that u is given of this form. Okay, this is exactly stated here in this proposition. And so what we are going to do now is actually to prove convergence, let's say, in the context of this element V and not of this element U. So first, but what we first have to ensure is that that even everything makes sense. So that if U is in the intersection of the domain of L and of the range of the operator L, then we should be able to insert somehow this this element U into fj of L and into f of L. Right? In general, you don't know whether these are bounded operators or not. It's also not assumed here in this first part of this lemma. So question is, can we even insert U into this into these operators? But we saw in this lemma 6.4 that if L is injective, then actually, and if E, this function E is a regularizer, which it is, then the intersection here is contained in the domain of these functions f of these operators f of fj of L and of f of L. So lemma 6.4 tells us that U is in the domain of f of L as well as in the domain of fj of L for any j in L in N. All right. Further, observe now the following. So let's say we insert now the operator L into fj and apply this to our element U. And we would like that this converges to f of L U, essentially. So this is somehow the question, whether we have a convergence here. Okay, and now we go over we change to the language corresponding to this element V, and further we need to employ somehow the definition of these operators here by regularization. And we know we can, for example, use this regularizer E here, and know then by the very definition of what this operator here is, that this is the same as the inverse of E of L applied to E fj. So we multiply E with fj and then insert L into this function and apply this to U. And then we use somehow this representation here of U as some element of V. So here we get some additional E of L. E is again an H0 infinity function, and this here is also an H0 infinity function. So we in particular know that we can commute these operators here, and this will cancel out this inverse operator here. So this is then the same as L inserted into the function E times fj applied to V. Okay, and we can do the very same here for these for the operator f of L. All right. So if we want to know whether this convergence here is true, we can somehow reduce this to the question whether for j to infinity this convergence here is true. Okay. And this can be done, as you will see, by the dominated convergence theorem. So we write out now all definitions, or the definitions here of these operators. And here we now have the advantage that we plug L into an H0 infinity function so that we can use Cauchy's integral formula here at this place. Okay, so we write E fj applied to L, now applied to this element V, and we can write this via the Cauchy integral formula over some path gamma, let's say over some angle psi, which lies between phi L and phi, and we integrate over E of z, fj of z times the resolvent of L in z, apply this to V and integrate with respect to z. Okay, we can do the same here for EF applied to L. So this would be E of z. We integrate over E of z times f of z times the resolvent of L applied to V and integrate this over z. And then what do you see? We know by the very assumption that fj of z converges pointwise to f, just by definition of f, essentially. Furthermore, you know that this here can be bounded in norm by what? So in the pointwise sense, we can bound this here by the modulus of E of z times, and then we know that the functions fj, they are uniformly bounded, right, in H infinity. So we can take here the supremum over all j and take the infinity norms. All right. And then we know that further L is some sectorial operator, so we can control this here, let's say, by some constant over the modulus of z. Okay. And now we have bounded somehow this this integrand here by some function which is integrable, because we have here this decay, or this bound by a constant over z. But here we gain some more integrability due to this regularizer E, because we get here some additional decay somehow in 0 and at infinity. So this is some L1 function which is independent of j, and we have pointwise convergence. So altogether we know that for j to infinity, this converges to this integral here by the dominated convergence theorem. All right. So this proves already the first part of the convergence lemma, namely that if U is in the intersection of the domain of L as well as in the range of L, that then we have strong convergence of these fj of Lu to this f of Lu. All right, and it remains to prove parts A and B here, but they are now a consequence of what we have already proven now. Okay. So let's say we prove now part A. Okay, so what do we know? We assume now that each of these operators, fj of L, is already some bounded operator, and we assume that each of these bounded operators strongly converge to T, and we want to show that the limit operator coincides with the operator f of A. Okay, so what do we know? Let's say we take our interpretation of the operator T as some linear relation. So we consider somehow these tuples here, U, T, U, for elements U, let's say in the domain of L, intersected with the range of L. Okay. And then we know, due to our part A, that fj of L already converges to f of L for all elements here in this intersection. But also fj of L converges by the very assumption strongly to this operator T. So this means that if I restrict T to the intersection of the domain of L and the range of L, then this is then this restriction is already the operator L, also restricted to this space. So we know that this is included into the linear relation f of A. Okay. So what else? So this is by our assumption. And let's say by the first part, we know that this inclusion here is true. Okay, but if this inclusion here is true, then we can also take the closure of the sets, and we still know that this inclusion is true. Okay. Here we know, for example, that f of L is a closed operator. This was proved in lecture 5. So this coincides simply with f of L because f of L is closed. Okay. And then we also know that the domain, so the intersection of the domain and the range is dense in the Hilbert space. This is due to proposition 2.4. This was already proved. So, so we know that this here coincides with the set of all tuples UTU where U is in H. Because T is a bounded operator and because this here is dense. So this is proposition 2.4. Okay, but this here is simply the operator T. Okay, so this is simply T. So we see that T is already a part of the operator f of A. But T is already defined everywhere, right? Because we assume that T is a bounded operator, so T is defined everywhere. So in particular, the domain of f of L is contained in the domain of T, and then they must coincide. So since the domain of T coincides already with the Hilbert space H, we find that T coincides with f of A. All right. So this was part A, and then part B is just a conclusion, or is just a corollary of part A. So what do we have to prove? We assume now that the operator norms of fj of L, that they stay uniformly bounded with respect to J. And then we want to conclude that the limit operator f of L is already a bounded operator, and we have the strong convergence here. All right. So what you know is that fj of L is a sequence of bounded is a bounded sequence in the space of bounded operators, and it converges by this part here. It converges already on a dense subset of H. So this is convergence on a dense subset or subspace of H. So, but if you have a bounded sequence of operators which converges on some dense subspace, then it converges everywhere by some elementary argument, which you know, for example, from functional calculus, functional analysis. So we know fj of L converges strongly also on the closure here of the intersection of the domain of L and the range of L, which is all of H. So it converges strongly everywhere. Okay. But the operator norms of fj of L, they are uniformly bounded by assumption, so the limit operator is definitely also a bounded operator. So we define some operator T as a limit operator, which comes from the strong convergence here of fj of L, and this operator is a bounded operator on H. Okay, but now we are precisely in the situation of part A. So we know now we have a bounded limit operator, and we have strong convergence of fj of L to this limit operator, and then part A just told us that T must already coincide with L inserted into the function f. So from part A, we know that T coincides with f of L. And in particular, fj of L then strongly converges to f of L, right? All right, and this is a proof of the convergence lemma. And I would say that this is a good situation to take a short break of 10 minutes, and then we continue afterwards with some examples. All right, so let's continue. So we now had some introduction of the bounded H-infinity calculus, and now we want to see some examples, which we do in section 7.2. And what you already saw in lecture 4 is that if you consider the Laplacian on Rn, then this operator has a bounded H-infinity calculus. So let's say we take some operator, we take L to be the negative Laplacian on Rn, which we introduced by the sesquilinear form, which test function space H1 of Rn. And this operator has a bounded H-infinity calculus. Of any angle phi between 0 and 2. Phi, all right. And we also saw in chapter 4 that if we take the operator norm of f applied to the negative Laplacian on L2 Rn, then this is bounded by the infinity norm of f on phi for any f which is bounded holomorphic. So this is what we have seen in theorem 414. Essentially, what we saw there is that we took some continuous function which should be continuous just on the real line and mapping into the complex numbers, and then we could already define f or the operator f of minus the Laplacian, and we showed essentially by Plancherel's theorem that we can bound this here by the supremum norm of f with constant 1 here. All right, this is due to theorem 414, and then in let's say example 514, we saw that the functional calculus that we defined for the Laplacian in chapter 4 coincides with the functional calculus we developed then starting from chapter 5. So, and in particular, we see that that we have bounded H-infinity calculus for any angle phi between 0 and pi. And this means if we take the infimum over all of these phi, we get 0. So we find out that the H-infinity angle of the negative Laplacian is just 0. Okay. So the next example is example 7.7. And I mean, we have our running example, which is a multiplication operator. So this example is again about the multiplication operator by some function f m. And actually, I'm just going to summarize what we are going to see. The details are left as exercise 7.3. So in exercise 7.3, we will see the following, namely, what do we know already? We know already from some other example that the multiplication operator associated to some function m is sectorial if and only if the essential range is contained in the closure of some sector as nu. And so this is something we already know. And what we also need is for the definition of the H-infinity calculus that the operator L is injective. So we somehow need to ensure that the multiplication operator itself is injective, and this is encoded by the property that M doesn't vanish almost everywhere. Okay, so these two properties here, they are equivalent to the fact that the multiplication operator associated to this function M is injective, and sectorial of angle nu. All right. Let's say nu is between 0 and pi. Okay. And then in this exercise you will also have to re-examine somehow this example 5.8, and you will see that as in example 5.8 we have that if we take some function decaying at 0 and infinity on some sector with angle phi, and this phi is between nu and pi, then we have that f of this multiplication operator here coincides with the multiplication operator associated to the function where we take the composition of f with this multiplication function m. Okay, this was in example 5.8, this was essentially proven for the Laplacian. Right there we had this multiplication function which was given by 4 pi squared times psi squared, and we verified this property, but this is true in general for multiplication operators, and you can just examine this example and see that this property here is true. All right, but if we can represent our functional calculus here simply again by multiplication operators associated to this composition here, we see by just taking norms that we can pull out the L infinity norm of this composition here out of the L2 norm, and we see that the H infinity calculus here is also bounded for this operator. Okay, so we see that the operator norm of the multiplication operator inserted into F, that this measured on L2, that this can be controlled by the L infinity norm here of this composition of F with M. All right, and this here is again controlled by this is less than the supremum norm of the function f, right? So this is less or equal than the supremum norm of f on the sector with the angle phi, right? M is mapping into the sector with angle nu. Nu is smaller than phi. So we see that in particular this L infinity norm here is controlled by the L infinity norm of f on the sector with angle phi. All right. So but we only have this representation formula. Let's say for h0 infinity functions, because there we can do the same calculation as in the example and with the Cauchy integral. And now we need to take it over to all h infinity functions, but this is exactly the corollary 7.5 that we already proved earlier today. So corollary 7.5 tells us that the multiplication operator associated to this function m has a bounded H infinity calculus, of angle phi, and again phi was arbitrary larger than this angle nu from the sectoriality. So in particular, we see that the H infinity angle of this multiplication operator coincides again with the angle of sectoriality of this multiplication operator. Okay, so this is the second example. And the third example we are going to see is about bounded operators. All right, so let's consider bounded operators. So, and I claim that if L is bounded, invertible and sectorial, then L has a bounded H infinity calculus. And the H infinity angle of L coincides again with the sectoriality angle of L. So let's see how we're going to prove this. And there's nothing better than a good picture. So let's just paint a picture at first. So what do we know? We know if we paint here the complex plane, we know that the spectrum of our operator L, it is somewhere here on the right. It is a compact set because L is a bounded operator, and we know that it lies in some sector. So it lies in some sector of angle phi L. And we know because of the invertibility, it stays away somehow from the origin. What else do we know? So let's say we take now some angle phi, which is larger than the sectoriality angle, less than pi, and we take some intermediate angle psi, over which we are going to integrate. So we have further things here. We have here, let's say, we have here maybe the angle psi, and let's say we have another angle, let's say here, phi. Okay. So this is the situation, and we can, if we take, let's say, some function, f, decaying at 0 and infinity on the sector of angle phi, we can represent the functional calculus or the application of f to L by the Cauchy integral formula, right? So, and for this, we would we would integrate here over the sector with angle psi. Okay, we come here from infinity and go back to infinity down here. Okay. So let's say we write f of L as a Cauchy integral here over this path. So we integrate over f of z times the resolvent in z. And what else can we do? There's already something we saw in the proof of Lemma 5.4, which was 2 weeks ago. What did we see there? Namely, we introduced other paths, which were called gamma epsilon r. So these paths, they somehow corresponded in cutting off the path where we integrate over. And then we walked here somehow in arcs around 0 and around the spectrum. Okay, so this here would be gamma psi epsilon r. And this orange path here would be gamma psi. All right. I hope you can still read something in this picture here. All right. So we took this. So in this example, we also took this this path gamma psi, and then approximated somehow our functional calculus here, our Cauchy integral formula, by these paths, by these finite paths over where we cut out the 0 and the point infinity, and we send here epsilon to 0 and r to infinity. All right. So what else can we do? You see here, if we take now the limit for epsilon to 0, so epsilon would be the parameter, would be the radius here of this inner arc, and r would be the radius of this outer arc. So this is r, and this here would be epsilon. And then you actually see, because our function f and the resolvent, they are holomorphic somehow in the neighborhood here of these arcs. So if you take two different epsilons, and if you compute somehow the difference between the arcs between one epsilon and another epsilon, you would have to integrate over an arc which only takes place somehow here in this neighborhood, right? But here every function we consider is holomorphic. Okay, and if we integrate over a closed arc over some holomorphic function, the result is 0 by Cauchy's integral theorem. And the same is here if we compare the path integrals over some big arcs here. The same argument applies, right? If we integrate over, let's say, a big arc somehow here, and if we close it, then we have here some closed path integral over some holomorphic function, and the result is again 0 by Cauchy's integral theorem. So this means that this formula here, or that essentially this limit here, coincides, or that these Cauchy integrals here, that they are independent of epsilon and r whenever epsilon is small enough and r is large enough. So we see that we can just throw away the limit here and then write that this is the same as 1 over 2 pi I, and we integrate over some fixed path of angle psi and parameters epsilon and r over the function f of z times the resolvent in z dz. And this holds for, let's say, for some epsilon small enough and r greater, let's say r greater 0 big enough. All right. And now this here was a crucial step now in the proof of the boundedness of the H infinity calculus of the operator L, because here in this situation, because we could somehow do this reduction to some path of a finite length, we somehow don't need the information that f decays at 0 and at infinity in order to make this integral here convergent. Right now, we just integrate over some continuous function over some compact set, essentially. And then we can take out the integrand simply in the supremum norm and don't need the decay of f at 0 or at infinity anymore. So, so what we see, what do we see? We can calculate the operator norm of f of L, and bound this by what? We can bound this by, we have here this 1 over 2 pi times the length of the path gamma psi epsilon r. And we also have to take the supremum norm over the operator norms of the resolvent of L. And we take z from this path gamma epsilon psi epsilon r. All right, this is just some constant. And we also take out the supremum norm of f here. So times the supremum norm of f. All right, and this here is just a constant. So we have here the length of the path over 2 pi times the supremum norm here of the operator norms of the resolvent, but also only over a compact set. So this is a finite number, and this here defines as a constant c. So, but this calculation was again just for h0 infinity functions f. But again, the corollary 7.5 allows us now to go over to all h infinity functions. So again, by corollary, we know that L has a bounded h infinity calculus of angle phi. All right. And the property, so I assumed now several things, namely that L is bounded, invertible, and sectorial. And essentially, what the sectoriality was actually only needed to ensure that the spectrum lies in some sector. You always know that if you, let's say, if the operator is bounded and invertible, somehow the spectrum is a compact set, and if it's invertible, you stay away from the origin, and then you know that for example, in the neighborhood of the origin, the resolvent is always just a bounded function somehow because it's a continuous function of on some compact set. And if you go far away from the spectrum, you know by a Neumann series that you can already bound the resolvent there by a constant times 1 over z. So essentially, this boundedness and invertibility and the property that the spectrum lies in some sector already implies that it's sectorial. So this sectoriality here is just an assumption on where the spectrum actually lies in the complex plane. All right. And there's another property which is of importance in some situations, namely if you have some operator L which has a bounded h infinity calculus, then this property is stable under taking adjoints. And this is what we prove in the next lemma. So let L be injective and sectorial, and let's say we take some angle phi between the angle of sectoriality of L and pi. And then L has a bounded H infinity calculus. If and only if L star, so the adjoint of L, has a bounded H infinity calculus. Of angle phi. I forgot to write here also of angle phi. All right. And in particular, if we take the infimum again over all angles, then we see that the H infinity angle of L coincides with the H infinity angle of the adjoint operator L star. So the proof is not too difficult. It follows by, let's say, some abstract nonsense that we proved already in the last weeks. Namely, what you want to show. Let's say we first assume that L has a bounded H infinity calculus of angle phi, and then what you want to see is, or what you want to estimate, is f of L star. And you want to take the operator norm of this operator. All right, but we know already something about the adjoint calculus. So we know already if we have here if we insert the adjoint operator of some operator L into some function, we can take this out by inserting L into the adjoint function f, and take the adjoint operator of this function. Okay, so this is essentially proposition 610, and then we know that the operator norm of the adjoint of some operator coincides with the operator norm of the operator itself. So we can just throw away the star here, and this coincides with the operator norm of f star of L on H. This is proposition was from the first week, proposition 120. Okay, and now we know we assume that L has a bounded H infinity calculus, so we can control this here by some constant c times the infinity norm of f star on the sector with angle phi. So this is assumption. Okay, but the supreme norm just is the same of f star or f. So this coincides with c times the supremum norm of f on the sector with the angle phi. All right, so we see that if the H infinity calculus for L is bounded, then it is also bounded for L star, and the reverse direction is essentially the same. However, so we would perform the same calculation, but use that we can write. So what we would start here with f of L, but there's no star here which we can take out, but we can use that that L can be written as the adjoint of L. Okay, and then if we use this identity here, we can start with f of L, write it as the adjoint of the adjoint, and then take out the star again to the function f. And then we are in a situation where we again evaluate somehow the function f star, and we insert the operator L star there. And then we can make the H infinity calculus for L star accessible in this situation. All right, so this is essentially the proof here of this duality principle for the H infinity calculus. And good. So we are almost over here with this lecture. I have a final warning here, namely the. So as I said at the beginning of the lecture, the H infinity calculus is not bounded for any sectorial operator. So there are counterexamples. Which we will not elaborate here, but there is a Hilbert space H and an invertible and sectorial operator that does not have a bounded H infinity calculus of any angle. All right, this is, for example, you can see for this work of McIntosh and Yagi from 1990. And this was elaborated further, for example, in the book of Hase, where you can read more about counterexamples for the H infinity calculus of sectorial operators. And usually in the usual situation, or let me say this as a last remark here, namely in the situation where you work with differential operators, it's not really known whether there exists some example of a sectorial operator which belongs to some PDE that does not have a bounded H infinity calculus. So usually if you are in some situation and if you study some differential equation or some operator associated to some PDE, then, and it is already sectorial, then let's say the probability that it also has a bounded H infinity calculus, they are very high. But if you could, for example, find some example of some operator associated to some PDE that is sectorial but does not have a bounded H infinity calculus, then let us know. All right, so this was it for today, and then we see us again for on Wednesday for the next lecture, and there we will have some important examples. So this is a main example somehow here of this lecture, which is about emigrative operators, and in particular we prove that any elliptic operator in divergence form has a bounded H infinity calculus. Okay, so thank you for your attention and have a nice day.